This worked example is a little bit of a long one because it's quite a difficult one in the sense that we're going to prove two different things. So the question there says prove the medians of a triangle are concurrent. So we have to understand what this word concurrent means. The word concurrent essentially means that they're all of the lines that we're looking at are going to intersect at a single point or at a common point. So what this is saying to us is to prove that the medians of a triangle intersect at a common point, and that point is going to be, in this diagram that we've drawn, we're going to call that point Y. So that's our intersection point. If we look at a theory that is well known for triangles, it's this one here. So first of all, what we're going to prove, the three medians of a triangle intersect at a common point, and also the fact that the distance from each vertex to this intersection point is 2/3 of the corresponding median length. Okay, what that means is if you were to look at the line, for example, here, that goes from A to A dash, and I'm going to turn that into a vector because we are in vectors. We're going to work in vectors. I'm going to make this a vector. Boom. If we look at this vector here, this part of the vector, A to Y, is 2/3 as long as this vector here from Y to A dash. That would be 1/3 as long, 1/3 again. So looking at this entire vector here as a length of 1, 2/3 of that vector is between A and that point of intersection with another median line, and on the other side you have 1/3 left over. So we're also going to show that as well, and in fact that's what we'll show first. So we'll show this idea, that if we divide a triangle up, I'm trying to get rid of that too, I can't get rid of it, in such a way as shown here, that you've got 2/3 and 1/3 either side of that intersection point. So first thing I'm going to do is I'm going to draw vectors for what I know. So I'm going to look at A to A dash and B to B dash. The point of intersection is Y. And the other thing I'm going to do here, just to help me out, which I'll do in green, is do some position vectors from an origin. So I'm defining the origin to be a corner of this triangle. So that way we can have these vectors O to A and O to B. Okay, so let's look at defining some things here. I'm going to call the vector O to B, or actually we'll start with O to A. I'm going to call that vector A, just to make life a bit easier. So that's vector A. And I'm also going to let the other vector, the position vector O to B, equal B. So this vector here is B. So I've got A and B. Okay. Then I've got some other vectors here. I've got A to A dash, A to Y, B to B dash, and B to Y. They're ones I'm also going to be working with. So I'm just going to copy this and put this onto the next page. And we can start looking at how we can use this information. So again, I'm just going to change colours. We've got B to Y and B to B dash. We're going to first of all show that B to Y in ratio to Y to B dash, so that's these parts here, is equal to the same ratio between AY and Y to A dash. And we're going to show that ratio is effectively 1, 2, 2 to 1. It's a 2 to 1 ratio. If I divide this up into parts, 1, 2, 3 parts, 2/3 of the parts are on this side, 1/3 of the parts are on this side. So this is a 2 to 1 ratio here as well. That's what we're going to show. So we're going to show that this is a 2 to 1 ratio. Okay, so that's part 1 of our proof. So the first thing that we're going to do is identify or write these vectors in a way that's a bit more sort of easily accessible to us. Okay, so the first thing is we know that B to Y, okay, is parallel to B dash. We know that, okay, and we also know that A to Y, so that's to there, is parallel to A dash. So what we can do is we can actually rewrite that then. So that means that we have B to Y can be written as some scalar m times B dash, and a to y can be written as some scalar n as a dash. So m and n are some real constants. Okay, we know that. The next thing we need to do is, well, let's define what these are. So b dash equals, if I actually look at where that is, that's here to here, that's this big red vector. Can you see that you could travel backwards along A? And remember that this b dash here, the way that we've defined this, b dash, a dash, and also this point x, they're all midpoints, okay, along this triangle. So this is a midpoint, this is a midpoint, and this is a midpoint. This is our intersection point y. So if we were to go backwards along here, and then along here to get from b dash to b, or from b to b dash, we'd be going half this distance of a. So to go from b to b dash, I'm going to go this way. I'm going to go b to o, plus a half of this vector o to a. And I know that b to o is backwards along b, because I've defined that to be b. And o to a, well, that's a, so this is a half a. So I know that. And also, same way with a dash, going from here to here, I could go again backwards along this vector, which is a, so negative a. And I should do negative OA so we can see it properly. And then going along this vector, remember this is a median point here, so it would be a half the distance of O to B. So O to A, remember, is A, so we'd go negative backwards along A and a half B. So we've defined B dash and A dash. The next thing we can do is we've got this expression here. So what we can do, I'm just going to copy this, is replace now B dash and A dash. I'll do that on the next page. So that implies, and just dividing this up with a line so we can keep it fairly neat, that B to Y equals and A to Y equals. We're going to use these expressions that we just found. Okay, so B to B dash, B to Y is M times this expression here, so negative B plus a half A. And A to Y, well, that's N times this expression here, negative A plus a half B. Okay, now what we need to do is we need to prove that these vectors here do satisfy this particular ratio. I'm just going to put a box around that too because that's what we're looking at. Now, if we want to prove this, we're going to need to work with what we have, by and ay, but we need to find some kind of link between them. So by to ay, if we have a look at our diagram here, by is here, ay is here. We actually could use other vectors in here as well to help us define by and ay. So I'm going to do these now in a different colour. I'll do these in purple. Okay, so oops, by and ay, we've got these expressions already. We can link these two together because if we think about this vector here, b to a, okay, b to y is the same as b to a plus a to y. So I'm going to use that on the next page. So we also know that, oops, b to y is equal to, and just looking at the picture again, b to y is the same as going b to a plus a to y. B to a plus a to y. And how can we express b to a? Well, let's check out what we've got here. B to a is given as, we could go backwards along this vector, negative b, and we could go positively along the other vector a. So negative b plus a. So we've now got negative b plus a for this part, and a to y, oh, check that out, we already know that. So that's n times negative a plus a half b. Okay, so we've got that expression. So now we know two expressions for by, and I'm going to just put a circle around them. This one, and also this one here. So what we can do, because we know that these two things have to be equal, we can now equate them. So equating these two things now, we've got, equating by, we've got m times minus b, so we've got negative bm plus a half m, I'm just going to write that as m on 2, a, equals, and now equals this side here. So negative b plus a, this is minus na, and this is a half n, so I'm going to write that as n over 2b. Now a and b, those two vectors, if we look at the diagram, you can see that a and b are not parallel, and hence they are independent. So because a and b are independent, we can equate their coefficients. So what that means then is that we can equate the coefficients of b. So if we look at the coefficients of b on each side, you've got negative m equals, on this side, a negative 1 plus n on 2. So they're all the coefficients of b. So that one, and that one. And we've also got for a, the coefficients are m over 2 equals 1 minus n. So we've equated the coefficients of a. What we need to do now is we've got two equations, and those two equations are going to allow us to find those two unknowns, which are m and n. So I'm going to use the CAS to do this. You could also use simultaneous equations, elimination or substitution. But using the CAS, I've got negative m equals negative 1 plus n on 2. Just going to go over to here. Okay, so I'm going to put in solve. I'm going to use square brackets as well, and then just put in my equations. So negative m equals negative 1, just go back again, plus n on 2, plus n on 2, and then the second one I'm also going to do is going to be m on 2 equals 1 minus m. So m on 2 equals 1 minus n. And we have to solve this system for n and for m. So if we push solve, you can see we've got 2/3 is the solution for n and for m, and that's really nice because that's going to work out really well here for what we wanted. So m equals 2/3 and n equals 2/3. Therefore, what we were trying to do here is show this relation and find what m and n are. So what we've got now is we've shown that by equals 2/3 of b to b dash, and that ay equals 2/3 of a to a dash. And if we think about it, that's exactly what we want to show, because we wanted to show that this distance here, a to y, is 2/3 of the distance between a to a dash. So what that means is that a to y in ratio to y to a dash is 2 to 1. So we've actually shown this is true. And I'll just put this back to where we were. So that's the first part done. And I'll just put that there so we've got a note to ourselves. Therefore, we've been able to show that ratio. It's a 1 to 2 ratio here. So a to y is 2/3 of a to a dash. Okay, so we've proved that. So knowing that we've proved that, now what we have to do is look at a vector here between O and X to show whether or not we end up with that intersection point there at Y, and to show whether that vector also is divided in a similar ratio. So I'm going to do this vector now in black. I'll start working in black for this last section. So there to there. Okay, so now let's work on this vector. So we've got two things to look at here, O to X and O to Y. The first thing I'm going to do is look at O to Y. So that's O to the middle. Okay, so we've got O to Y equals, looking at the diagram here as well, I'm just going to copy this over so I don't have to keep coming back to here. Again, you can create O to Y using information that we already have. So for O to Y, we could travel. If we think about it, that's exactly what we want to show, because we wanted to show that this distance here, A to Y, is 2/3 of the distance between A to A dash. So what that means is that A to Y in ratio to Y to A dash is 2 to 1. So we've actually shown this is true. And I'll just put this back to where we were. So that's the first part done. And I'll just put that there so we've got a note to ourselves. Therefore, we've been able to show that ratio. So it's a 1 to 2 ratio here. So a to y is 2/3 of a to a dash. Okay, so we've proved that. So knowing that we've proved that, now what we have to do is look at a vector here between O and X to show whether or not we end up with that intersection point there at Y, and to show whether that vector also is divided in a similar ratio. So I'm going to do this vector now in black. I'll start working in black for this last section. So there to there. Okay, so now let's work on this vector. So we've got two things to look at here, O to X and O to Y. So let's express both of those vectors using the information that we know. So I've got the vector here, the vectors here, so I've got O to Y. Now you could express O to Y by going along O to A and then going down along this part here, A to Y. Now we know already that O to A is this vector A, we've called it that. And we also know that A to Y, remember we found that that was 2/3 of the vector, which is A to A dash. And we also know A to A dash because we were able to give that in this form here. So A to A dash, which was this. So negative A plus a half B was A to A dash, negative A plus a half B. So that's O to Y. The other thing I'm going to look at is O to X, which I've got there. So O to X you can again make by going along O to A and then going along this way, A to X. Okay, now knowing that A to X is half of this vector, and you can see I've written what that vector is here, negative B plus A is that purple vector. O to A is A, so we'd be going against the flow of this vector, so it would be negative half of this. So negative a half of, negative B plus A. So that's the same as A plus a half B minus a half A, which equals a half A plus a half B, which is a half outside of A plus B. So that's what we find OX to be. And if I also look at O to Y, what I can find with O to Y is, again, expanding this. We've got 2/3 of A. This would be plus 2/6 of B, which is the same as a third. A minus 2/3, that's 1/3 of A. And 2/6 is 1/3 of B. So what you can see here is that O to Y, if we look at them now factorised, is 1/3 of A plus B. O to X is a half A plus B. Okay, comparing these, we want to show that the vectors O to Y and O to X are also in this ratio. So O to Y equals, if we think about, we want to show this, is O to Y equal to, as a ratio, O to X, 2 to 1. This is the same as saying, okay, is this vector O to Y, is that the same as 2/3 as long as O to X? And you can see here, 2/3 times O to X would be a half, which equals 2's cancel, 1/3 of A plus B. And that is what O to Y already is. We know that. So what we've shown here is that, yes, O to Y is 2/3 O to X. That is, O to Y is to O to X in ratio 2 to 1. Okay, so because we know that, we've now shown that all of these vectors here, okay, are in a 2 to 1 ratio. The other thing that we've shown as well is that since there's this relationship between OY and OX, OY is also, parallel to OX. So ultimately what we've been able to show from this diagram is that OY and OX are also collinear. So to finish this off, I'm just going to get rid of this section here. So OY, the points which were X, Y, and O are collinear. That is that they sit in the same straight line of points and are in that ratio that was required, which was 2 to 1. 1 to 2, the way I've done it. So what we've shown is what we meant to show, which was that the three medians, okay, all of them lie, all of those points, so for example, OYX, BY, B dash, and AY and A dash, they all lie in the same line, they're all collinear, and they're all in that 1 to 2 or 2 to 1 ratio. So what we can say to finish is that the medians, are concurrent at Y. So a very, very long proof, that one, because it has quite a few parts to it. The key thing there is identifying what you're looking for and then being able to work with a range of vectors to show what you need to show at the end of that proof.